Welcome to Convergence. My name is Michael Doran. I'm a California attorney. I don't have a dog in the hunt. Today we're going to talk about Hurricane Michael, 2018 storm that landed on the panhandle of Florida on October 10. Albert Einstein stated that among the most difficult problems in all of physics is the Earth's magnetic field. I'm a California attorney, and I'm going to just argue that the Earth's magnetic field is among the most difficult problems in all biology. This tropical storm, as you can imagine, I'm going to talk about it in terms of an electrical complexity. What I've learned about these storms is that they seem to do very well depending upon the electrical conditions, what's coming into the atmosphere from space, and how the Earth takes those electrical conditions. Also, carbon dioxide comes out of the ocean. It's like taking a beer or soda and shaking it and cracking it open. The surface flow and the winds and the agitation bring carbonation out of the ocean and bring it up into the clouds. And there, especially when you get at higher elevations, 30, 40, 50, 60,000 feet, cloud droplets get in a state where they're supercooled. And how fast they freeze in the context of the incredible electrical fields that are inside tropical storms determines how organized the storm is, how it vents, and how it stacks. This really changes concepts of, for instance, shear that meteorologists talk about when they are describing what's going on with a storm. This particular storm occurred in a period of high cosmic rays. If you go to spaceweather.com, they have an interesting feature where you can look into the archives and see what space weather was on a particular day. And at the same time, they were starting to develop a very detailed description of what space weather was in terms of cosmic rays. What cosmic rays is the solar system, the suns and the stars, basically the stars in the solar system, they emit radiation. And we're in the plane of the Milky Way. In fact, there's been some studies that have correlated glacial periods of where the Earth is up and down as it makes this 30 million year oscillation up and down in the plane of the Milky Way. And that's because as it gets into the plane, there's more cosmic rays than when it's higher up in the plane of the Milky Way. And that probably has to do with how particles interact with gravity when you get into a plane, and that would increase the amount of cosmic rays as you line up in the plane of the Milky Way. So what happened on that day? Well, according to Cosmic Ray Station, which is at the University of, I'm not even going to try to pronounce it, it's OULU, which is in the Hawaiian Islands. And in October 2018, we were at a very high period of cosmic rays. And the scale that they have is 10, 5, 0, minus 5, then all the way down to minus 20, which was in 1992. So really from, there was a little dip in at the end of 2017, but then it rose up, and so basically from the time that we had the car fire here in Reading to 2021, it's been at this level well above 5, and probably in the close to 10 at some points in 2020. So what did that mean? Well, what it means is essentially these particles create all kinds of ions and electrical particles in the upper atmosphere. And, pardon me, it's exactly what we had in October of 2018. More specifically, the mechanism of why we have high cosmic rays is because the sun is quiet. And we had numerous days on end of no sunspots in 2018. And that was no different in October of 2018. And before I get into that, let me also talk about the fires here in California. So this is before the fire in Paradise, which was in the next month. So this is October, and I also, in the previous video, talked about a record-long lightning strike that went across South America on Halloween. So a couple weeks before that. And so this is the time of year where you're starting to get a lot of lightning in South America. It's their springtime, and yet you still have warm tropical waters, especially in the Gulf of Mexico. And you still have a little bit of lightning in the northern hemisphere. Certainly have lightning in the intertropical convergence zone along the wider part of Africa. It hasn't fallen down to the narrow part. There's a tremendous amount of lightning globally. There's a double peak of lightning. The greatest peak is in the springtime in the northern hemisphere. But then there's another peak of lightning. So you have high lightning across the globe. And you have high cosmic rays that facilitate this kind of plasma behavior and the potential differences. So what happened that was odd? Well, just a couple of odd things in terms of space weather. Again, from this site, you can, at spaceweather.com, you can go to an archive. And on October 8th, which is a couple days before landfall, it was still a tropical storm, they were predicting a G1, that there was a high chance of a G1 geometric storm. And the sun was blank, there was no sunspots. And the highest X-ray activity was at A1, which is very low. But it had been low like that for some time. Now, just because there's no spots in the sun doesn't mean that you don't have a coronal hole, which is why there was a sunspot activity. Which is why there was a geometric storm forecast, because there was in fact a coronal hole. And again, you can see this with your own eyes if you go to the archives and look up that date. And so they were predicting solar winds coming from this coronal hole, and in fact they were elevated that day. They were not hugely elevated, but enough. They were at 539.2 kilometers per second, and the density was 5.9 protons per centimeter squared. Now, I don't want to be made a liar of, but I've observed these storms for a long time, and notice that tropical storms are not as aided as much by solar winds when they get over 500 kilometers per second. And this is just a little bit over that, and with some decent density. So the next day, and this is when the Michael had turned into a tropical storm. The next day, October 9th, then the solar wind, the speed was up a little bit, but the density was down. The speed was up to 565.3, and the density was 5.2 protons per cm squared. Now, another thing happened. So there was a A2 X-ray solar flare that probably came from that coronal hole, because there was no sunspots. And that's not a nothing X-ray activity. It's a little bit of X-ray activity. And then there was a G1 I'm going to read right from the site. Sparking a G1 class geometric storm in southern Finland, the night sky turned green as energetic particles rained down on the upper atmosphere. Professor Maitis Untuke Lane of Finland's Aalto University went outside for the show to watch and listen. He has some recording advice, and if you go to space weather, you can actually listen to what is a type of geometric storm thunder that occurred on October 9. So it was more than nothing going on in the upper atmosphere near the pole in Finland with this particular geometric storm. Finally, the day of landfall, and this land fell at 160 miles per hour, and it was, as far as barometric pressure, it's like the 10th strongest. As far as wind speed, it's like in this particular era, and consider that fertilizers and so forth are flowing down the Mississippi, that this is really its own era, given the types of changes that have occurred, whether you're talking about mining in the Iron Range in Minnesota and the depletion of iron there. It's apples and oranges in a lot of ways to compare this storm, Michael, with, say, Camille or the storm that hit the Florida Keys. It's hard to talk about and compare these storms when so much has changed, including atmospheric carbon dioxide. But this is a very powerful storm, and it rapidly intensified as the solar winds died a little bit. So on the 10th, the actual day of landfall, and they use universal time, so there's about a 5-hour difference, but essentially the landfall occurred right as you were turning from the 10th to the 11th. But on the 10th, solar winds were down to 521 kilometers per second. So 21 kilometers per second faster than this threshold that I talked about. So I think that the solar winds, a tiny bit might have been affecting this storm, but there were other things going on. And then finally, to offset that, there was a B1 X-ray event, which is another level, and it's part of making electrical particles that the storm organizes. And again, it's this idea that it takes energy to put high pressure together, it takes energy to put low pressure, low and high pressures annihilate each other, and to put positive charges in a concentration, it takes energy. To put negative charges together, it takes energy, and they annihilate each other. What keeps them all apart with the same order is water, because Water is a powerful dielectric. It prevents electric fields from passing, and water is also what drives storms. It's the latent heat from the ocean that's used to make clouds. So electrical conditions organize the storm and at the same time affect microphysics and how fast does a supercooled water droplet in these electric fields go to ice and create heat-trapping cirrus clouds. Okay, so then on the 11th, which I think is interesting, and it's especially as you're really denoting that the solar winds were dying down, they did go under 500 kilometers per second, and the density thinned out. It was 449.7 kilometers per second on the 11th, and 4 protons per centimeter squared. Okay, so let me talk about the biological part of it, because as I've just stated, Einstein's problem of modulating or dampening the Earth's magnetic field is both electrical and biological. So your magnetic field is necessarily an electrical phenomenon. So here we were in California. We were under smoke clouds all summer, starting from the fire that caused me to leave my house on the 26th of July, 2018. But also there was a giant fire south of us, one of the biggest, and at the time the biggest complex fire in state history. And just kind of as an analogy, the pool at our house that we had to evacuate turned just gross with algae, because you have all this smoke that gets into the pool water, and it's like a boon it's fertilizer for algae. And so one question that you can talk about in terms of carbonation in the Gulf of Mexico is, well, what was the dead zone like? Well, it's a little unusual. 2018, the dead zone was actually less than normal. And so, for instance, this report here was talking about researchers at the Louisiana State University talking about the dead zone. And they, in the beginning of the year, they'd predicted that it would be 6,570 square miles, but it wasn't. It was quite a bit less than that. It was from July 22nd to 28th, they mapped an area of 2,020 square miles, about the size of Delaware and smaller than predicted. It was well below that 5,770 square miles. Average from 2014 to 2018, and only a third the size of the hypoxic zone ever measured, which was 8,776 square miles in July 2017. What they speculated was that there were sustained winds from the west that may have pushed the low oxygen water to the east, which is where the Hurricane Michael landfell. It landfell in the panhandle of the state of Florida, and Mexican Beach is where it landfell. And so you had a contribution of something from the Mississippi in terms of nutrients to start blooms. But what did we really have there in the fall of 2018? This is from the official website of the United States government on harmful algae blooms under hazards, Florida 2018 event. And what did they say? They said there was a red tide that occurred starting from October 2017 and spread to the panhandle and the east coast of Florida. A short-lived bloom also occurred in Texas in September 2018. Red tides caused by Carinio brevis algae produce toxins that can kill fish, respiratory irritation, mortality of sea turtles, manatees, birds, and dolphins. So what happened is there was a red tide where the storm landfell and all along the Florida coast. And I think, did the fires have anything to do with it, and the smoke blowing across the country and then down rivers and affecting the algae in the Gulf of Mexico? I would, but that was my pool, and I don't know necessarily whether the tides were related to the fire, but I can tell you that there was a red tide where the storm landfell, and that what happens is it affects carbonation, and that's the mechanism here is carbonation and electrical. The more carbonation that you have in a storm, the more you're going to get an organization from that. The more electrical conditions that favor the cloud microphysics, creating these asymmetrical cirrus clouds, the more you're going to have organization. They also said that regarding the algae bloom currently affecting Florida, appears to have intensified and spread to the Florida Panhandle after Tropical Storm Gordon in September 2018. So this is the nature of a feedback, right? Because what happens is tropical storms stir up the oceans and bring nutrients up, and then the nutrients support more phytoplankton and other bloom events. So which then in turn produces more tropical storms. It's a feedback, it's a dampening. And the reason that it occurs in the first place is because there's an electrical imbalance on this living Earth. The balance is all tending towards modulating or dampening the Earth's magnetic field. Okay, and the final thing I want to talk about is the SOI index. And what that is and the Australians have had a handle on this for a long time, and what they've noticed is that if there's an El Nino or a La Nina, it affects their cattle runs in their very arid country. And so they started monitoring Tahiti and Darwin for barometric pressures and an index. There's more going on there in terms of the undulations that come off this. It's a teleconnection event, La Nina. And what I've noticed is that when you have a rising SOI index, it really favors, even on a daily level, if you have a raising index, you're going to have conditions that, and the way I describe it, it's like putting on silk stockings, walking across a carpet and touching something metal where you cause a zap. And that's what happens in the tropical Pacific when you have this index moving across the Pacific towards the Americas, and lightning collects and moves across the Pacific in an easterly direction, and then that potential difference moves into the Americas and allows these capacitive couplings over tropical storms. And what you had in October of 2018 was a very strongly, sharply raising, even on a 30-day value, which this graph here is, in October of 2018. And then on October of 31st, so Halloween of 2018, that's where the GOES satellite picked up the record long lightning bolt in South America, where again the source of these electron precipitation and all what powers these storms, this particular part of the complexity, the electrical complexity of them, would come from South America. It's a large-scale type of phenomenon. Okay, and then one more thing I want to talk about is the image that goes with this video, it's an image of, and I've watched numerous infrared of this particular storm, and followed it, and there's a super rest reflectivity tilt 1, 6:02 Pacific Daylight Time of the storm, showing mesovortices. There was 5, and then little higher frequency waves really around the whole storm. And that's the thing I noticed the most, especially as it got close to landfalling. There wasn't, it was almost square shape as it's circling around, probably 4 mesovortices. But especially as it got close, and it was a category 5, 160 mile an hour winds, as it got close to the panhandle of Florida and Mexican Beach, it was almost perfectly round except for these little jagged waves on the inside of it. I believe those are undulations and indicative of electrical energy transferred to within the wheel of the storm. Very round, remarkably round, except for those little jagged edges. And you know, think about it. It's 160 miles an hour moving around in there, and yet you have these little jagged edges all around in a circle, in almost a perfect circle. There's nothing in nature, there's no ambient winds that are going to create that type of resonance. Perfect sine waves inside a circle. The only thing that can do that is electrical. And that's exactly what you saw with this particular storm. Okay, that's my analysis of Hurricane Michael. And the most active year that's going to come after this, it's important to talk about 2019 is not as active because it was an El Nino year. 2018 and 2020 were both La Nina year. You have decarbonation in the Pacific that supports these tropical storms. And so it's very important to talk about that. But you started to get, in 2020, more X-ray activity, and there wasn't much of a forecast for intense storms in 2020. There's one I'm thinking about pretty close in track to Michael that absolutely blew up and rapidly intensified with an X level X-ray, and the forecasters just totally blew that, missed that. And I think part of that confusion about what X-rays do to these tropical storms and why they're not noted in forecasts is because you're going to get these cosmic ray storms, which is on the other end of electron creation versus proton creation. And I think this storm is notable as a totally blank sun, no sunspots, and it produced this massive, devastating storm. Okay, thank you for watching. Please click like if you like. Please, I would appreciate all the sharing of this that's possible. Please join. Thank you.